Hey guys. Um, Yesterday we talked about the history of the atom and how we came to our modern understanding of atomic structure. And what we're going to talk about today is a little bit more detail about what goes into that structure of the atom. Where are the protons? Where are the neutrons? How much mass do they have? What charge do they have? What's their relationship to the electrons? And how is all of this information displayed on element symbols and the periodic table? So we are in your packets on page, oh gosh, I don't know, 6, I think. Um, and you're going to want to pause this video from time to time as you need to take notes, because I'm obviously not going to, put in these big long wait times for you to write down these definitions and to fill out the charts. So listen to what I have to say, give it a pause, and fill out your notes. Here we go. All right, so we talked about the Greek word atomus, meaning indivisible, and that's where we get our definition, or our word and the definition of the atom, which is the smallest form of matter that maintains an element's properties. So of course we can break down matter even farther, right? So Dalton's, theory of matter saying that atoms are indivisible is no longer totally true. Like, we do know that we can break an atom down into protons, neutrons, and electrons. And we know that we can break an atom down in a nuclear reaction and get energy out of it. But once you break an atom down any farther than itself, if you make a split to that nucleus or a change to that nucleus, you then lose the properties of that element. So atoms are the smallest form of matter that maintains the properties of that matter. We also talked about the nucleus. We looked at the gold foil experiment and how Rutherford discovered the presence of a small, dense, positively charged nucleus. And so, of course, that is where the protons exist. And we now know, based on the work of Chadwick, that this is also where the neutrons exist. And we'll talk about the difference between protons and neutrons here in a little bit. The model of the atom that we're working on thus far would be called the nuclear model, or the Rutherford model of the atom. So I want you guys picturing a nucleus with the protons and the neutrons on the inside, and the electrons spread out around it in that mostly empty space, right? So these atoms are really huge in terms of their radius. Well, they're not. They're tiny, tiny little things. But when we're talking about the size of the nucleus versus the radius of the entire atom, most of that atom is, in fact, empty space. These electrons are very, very tiny and are quite spread out compared to this densely packed positive nucleus. Okay, so let's compare and contrast the 3 subatomic particles that we now know to exist. Obviously, the protons have a positive charge and are located in the nucleus. Now, we say the relative charge as a 1 plus because that's not actually the coulombs of charge on the electron or on the proton. All we really care about for our purposes is that protons and electrons have equal and opposite charge. So we say that a proton has a 1 plus charge and an electron has a 1 minus charge. And of course, the neutrons are neutral. Now, same thing kind of goes for mass. Like, I've shown you the actual mass values here. Like, you can see here, the mass of a proton and the mass of a neutron is like 10 to the negative 24th grams. These things are really, really tiny. But we don't, necessarily need this teeny, teeny, tiny number. We care about their mass relative to each other. So we say that the mass of a proton is 1 AMU, which stands for atomic mass unit. We say that a neutron is also 1 AMU, even though you can clearly see they're actually off by a little bit. They don't have the exact same mass. And what I want you guys to notice is that electrons are almost 2,000 times smaller than protons and neutrons. If we look at this relative mass of the electron, it's 1 over 1,840. It's like a fraction, a very, very tiny fraction of the size of the protons and the neutrons. Okay, so you get your protons and your neutrons in the nucleus. They're very heavy. The protons have a positive charge. The neutrons have no charge. Outside of that Nucleus is mostly empty space where the electrons are flying all around. We'll spend a whole unit talking about where the electrons are and how much energy they have. But relative to the protons, the electrons have that equal and opposite magnitude of 1 minus. Okay, so a couple more vocabulary terms for you guys to be aware of. The number of protons in the atom is called the atomic number, and the variable for that is Z. The atomic number is the number that determines the identity of that element. Okay, so hydrogen has an atomic number of 1. Helium has an atomic number of 2. Lithium, 3, etc., etc. So as we go across the periodic table, reading it left to right and top to bottom, it is organized by increasing atomic number, which is your number of protons. Change the number of protons, you've got a totally different element. The mass number is the total number of the protons plus the neutrons in the nucleus. It is always a whole number. You will not find the mass number on the periodic table, okay? You will find something called the average atomic mass on the periodic table, but you will not find the mass number. And these two things are related, and we'll talk about it a little bit more when we start talking about isotopes. But for now, the mass number, here's your equation, is your number of protons plus your number of neutrons for that particular isotope of that element. And it's always going to be a whole number. And you are not going to find it on the periodic table. So here we go with this conversation about isotopes. Isotopes are atoms of the same element. So if they're the same element, they have the same number of protons, but they can have differing numbers of neutrons, which is a little weird, I know. Here's an example. Let's say I have an element carbon, or an atom of carbon. Carbon always has 6 protons. That's what makes this carbon. Let's say this particular atom of carbon also has 6 neutrons. That would make this isotope of carbon what we call carbon 12. This is the isotope carbon 12. However, there is another isotope of carbon that exists. There are atoms of carbon that have 6 protons and also have 6, nope, that's exactly what I just said. So not 6 protons and 6 neutrons. Undo. Oops, because I have to erase. There we go. Let's go back to my pen here. Let's say we have 6 protons and 8 neutrons. Add those two together, and I get carbon 14. These are 2 different isotopes of carbon. They're both carbon because they have 6 protons. That's what makes it carbon. But if you have differing numbers of neutrons, you have 2 different isotopes. And you can see that I wrote those 2 different isotopes with like a dash and the mass number. That's one way to write it. Another way to write that isotope would be carbon with a 12 up at the top left, and carbon with a 14 up at the top left. Okay, so mass numbers can go up at the top left of an element symbol, or they can be written with a dash and the mass number to the right of the element symbol. And that's always going to be your protons plus your neutrons. These 2 isotopes of carbon have very similar properties, right? Like they, other than their mass being different, they behave mostly the same way in terms of their bonding, their boiling points and melting points. What will differ, however, though, sometimes is their radioactivity. Carbon-14 is radioactive and carbon-12 is not. We'll talk more about that later in our unit when we talk about radioactivity and carbon dating. Okay, moving right along. So what is that mass that you'd find on the periodic table, right? So remember I told you mass number is not on the periodic table. What is on the periodic table is something called atomic mass. And atomic mass is a weighted average of all of the isotopes of that element. Here's what a weighted average is, okay? The atomic mass that you see on the periodic table is equal to the decimal of the percent abundance times the mass of that particular isotope, plus the decimal of the percent abundance times the mass of the other isotope, for as many isotopes as you have. So, for example, I was talking about carbon-12 versus carbon-14. Percent abundance is how much of that isotope exists in nature. So, for example, carbon-12 makes up about 99% of all carbon in the universe. And carbon-14 only makes up about 1% of all of the carbon in the universe. So if I wanted to calculate what the average atomic mass of carbon is, I would need to take these percentages into account. Like, I would not calculate carbon's mass by going 12 plus 14 divided by 2. Like, that would give me an average of 13. But that is not the mass of carbon on the periodic table. It does not have an average atomic mass of 13, because we actually take into account that most carbon is carbon-12. So here's how we would calculate it. The decimal of 99% is 0.99 times the mass of this particular isotope, which we can just say is 12 AMU. Oops, I didn't write my units. Forgive me. Plus the decimal of 1% is 0.01 times the mass of that isotope, which is 14. Now, these masses can be measured more carefully, like if we do the actual mass of the proton and the neutron, but we can just use the mass numbers in this case. And so if I go to calculate this, I don't believe that I put this as an example problem, but you can just smush it in somewhere in your notes if you like. And I'm going to add that to, I get an average atomic mass of 12.02 AMU. And if you go look at your periodic table, you're going to see carbon's average atomic mass, I think it's 12.01, so this is probably like 99.5% or something. But we're pretty close, okay? So the number on the periodic table, you guys, is a weighted average. It is not just a straight up average. It is a weighted average of all of the different isotopes that exist, okay? Now, the unit that I'm using here, this atomic mass unit, is what we call the mass of one proton and the mass of one neutron. Where did it come from? Well, it just happens to be 1/12 of the mass of a carbon atom. So we often use carbon as our standard for most things. One, because carbon-12 is very stable, not very reactive. It's found in all living things. So oftentimes in chemistry, you'll see carbon as your standard for comparison. That's just where we got the AMU unit from. Okay, let's take a look at some element symbols here. This is a standard symbol that you might find on your periodic table. Your periodic table is slightly different. Every periodic table is different. Always just go look at your legend. On this particular periodic table, obviously up at the top, we have our element name. This whole number that you see, remember, the only whole number you're going to find on there is your atomic number, which is your number of protons. H is your element symbol. And remember, this mass value here is not the mass number. This is your average atomic mass. Sometimes it's just called atomic mass. And remember, this is a weighted average of all of the isotopes. However, we're not always working with periodic tables. Oftentimes, we're just writing element symbols ourselves. So here's an example of an element symbol that we would use quite often in chemistry class. Here you have, obviously, oxygen, your element symbol right here. The atomic number always goes here on the bottom left. Okay, this is always your number of protons. Remember how I told you could tell what isotope you were talking about by writing your mass number up here on the top left, right? So atomic number always goes bottom left. Mass number always goes top left. And that's going to be your number of protons plus your number of neutrons. Now, sometimes you're going to see a charge written up here on your top right. The way that atoms get charge is by gaining or losing electrons. So normally, your number of protons and your number of electrons are equal, right? So if I just had a neutral atom of oxygen, right, my protons would be 8. My neutrons, based on this mass number right here, protons plus neutrons equals 16, so my neutrons would also equal 8. And my electrons would equal 8 because my positive protons cancel with my negative electrons, making it neutral. However, if I look up here at this 2 negative charge, that must mean that oxygen has 2 more electrons than protons. This particular atom must have gained 2 extra electrons. So if I were doing the protons, the neutrons, and the electrons for this atom, 8 protons, 8 neutrons, 10 electrons, okay? Or you can just do a subtraction. Protons minus electrons will equal charge, right? So I see here, 8 protons minus 10 electrons gives me a negative charge. I don't often do it as an equation. I just think about it as canceling charges or balancing charges, okay? And we can't gain or lose protons because that changes the identity of the atom. We can only gain or lose electrons. And when we do gain or lose electrons, we now call this substance an ion, an atom with charge. If something has a positive charge, it's because it lost electrons, and now it has an imbalance of more protons than electrons. Okay, so be thinking about these symbols. Really important to remember: atomic number, mass number, charge. And if there's no charge written, it means it's neutral. Okay, this example is not in your packet, but let's just go ahead and do it together just for fun. All right, so our atomic number is our bottom left number. So our atomic number is going to be 9. Our mass number up here is 19, top left. Number of protons is your atomic number, so that's 9. Number of neutrons is going to be your protons plus your neutrons making up your mass number. Okay, so if of this 19, 9 of them are protons, that must mean that 10 of them are neutrons, right? Because this number right here, 19, is equal to your protons plus your neutrons. And if your protons are 9, it means your neutrons must be 10. Here, number of electrons. Normally, if I had 9 protons, I would have 9 electrons if this atom was neutral, but it's not. It's got a 1 minus charge, which means it has 1 more electron than protons. 10 electrons. This must have gained 1 electron to become this 1 minus ion. Oh, look, I had the answers right there. Let's do another one. Again, I don't think this one's in your practice sheet, but just bear with me and go through it. Atomic number, 35. It's your number of protons right down here, bottom left. Your mass number, 80 on your top left. This right here is your mass number. Your protons plus your neutrons have to add up to your mass number. So if my protons is 35, that must mean that my neutrons are 45 in order to add up to that 80 for that mass number. If there's no charge written in this top right corner, that means my protons and electrons are the same. 35 electrons. Okay, Now we are on to the practice problem that is actually in your packet. So go ahead and pause this video, work through this practice problem, and then come back to me and see if you got it right. All right, welcome back. An element has an atomic number, oh, there's an extra space there, that's annoying. An element has an atomic number of 34. That is my number of protons. And a mass number of 78. So if I have 78 minus 34, that must mean that I had 44 neutrons. And a charge of a 2+. That means it has more protons, 2 more protons, than electrons. So the number of electrons needs to be 32. For my complete element symbol, I need to go to my periodic table and I need to find out what element is atomic number 34. I'm checking my periodic table. I think it's selenium, but don't quote me on that. Yes, it is. Look at me go. Selenium, atomic number 34. I'm going to put my mass number, not my number of neutrons, but my total mass number up in the top left to tell me what isotope we're talking about here, and the charge of a 2+. Okay, so remember, for your ions, a positive charge means you lost electrons. A negative charge means you gained, well, not you, the atom, gained electrons. Okay? I know that's confusing for some people because you see a negative as a subtraction, and I don't want you to see it that way. I want you to see a negative as a negative charge. You gain something with negative charge, you're going to have negative charge. You lose something with negative charge, you're going to have a net positive charge because of those protons that remain. Okay. Now, we are going to have a longer conversation about isotopes in class together. So I'm actually going to stop here, and I want you guys to do some practice on the worksheet that comes next in your packet. Don't care about that. Your worksheet looks like this, okay? I'm going to check my recording, make sure you can see what I think you're seeing. Yes, very good. All right, so I want you guys to practice identifying numbers of subatomic particles on this worksheet. So you're going to obviously need your periodic table. And I want to kind of walk through a few of these examples with you because, because this can be a little bit confusing just because of this particular worksheet. Okay, so obviously your atomic number is your number of protons, right? You're going to get that number right off of the periodic table. So everybody look at your periodic table, go find hydrogen on your periodic table, find the atomic number, it's 1. And that is obviously how many protons you have, so you can fill that out as well, right? Your number of protons is always equal to your atomic number. For the atomic mass, your periodic table goes like way far out into multiple decimals. Let's just go to the hundredths place on this. So if I look at my periodic table to the hundredths place, I get 1.0, oops, you know what? It would be 1.01 if I was rounding. A-M-U. Ooh, this looks like a murder scene. Oh well, sorry. All right, now here's the tricky part, right? So the atomic mass you just get off of the periodic table. The mass number is not on the periodic table, right? And if they don't give you the mass number on this symbol, here's what I want you to do. I want you to just take your atomic mass and round it to a whole number. Okay, so for example, if you look down here at this carbon example, here they give you the mass number. They tell you what isotope they're talking about. So you would just write, for this one, you would just write 12. And for this next example, for lithium, they give you the mass number of 7. But for this one, they don't give you the mass number. So if you are not given the mass number, I want you to just round. whatever your average atomic mass was, to a whole number. Doing that is making the assumption that you have the most common isotope of that element. Like the reason why hydrogen's atomic mass is so close to 1 is because the most abundant isotope of hydrogen is hydrogen 1. The reason why carbon's average atomic mass is so close to 12 is because carbon 12 is the more abundant isotope, right? That's what it means to be a weighted average. Okay, so let's keep going. That's the only tricky part, is just like if you're not given a mass number, just round the atomic mass. We're just doing that for this worksheet. You'll always be given a mass number if you need it. Okay, so here we go. Your mass number is equal to your protons plus your neutrons. So here I have no neutrons. It's possible to have no neutrons, right? In fact, the most common isotope of hydrogen has no neutrons. And for your electrons, I want you to compare your protons to your electrons. Compare those two things and look at the charge. Here, there's no charge. So that must mean my protons and electrons are the same. 1. Let's do another example together. Here's hydrogen with a 1 plus. This is a hydrogen ion this time. Atomic number, 1. If it's hydrogen, that's its atomic number. Can't gain or lose protons. Atomic mass is the same. Oh my gosh, I don't know why it's doing that to my letters. It's terrible. Okay, remember I said if you're not given a mass number for that particular isotope, just round. So I have 1 proton, right? My atomic number is 1. My protons plus my neutrons add up to my mass number, so no neutrons again. But this time I have a positive charge. How is it that this atom has a positive charge? It must have lost 1 electron. So now it has none, right? See, if you have 1 more proton than electrons, you're going to have a net positive charge. Let's do 1 more. Maybe let's just do 2 more together. Look, I'm doing like all your homework for you. I shouldn't be doing that, but it's bothering me that I filled 2 of these out. So now I have to keep going. Your teacher's not type A or anything. All right, here we go. Atomic number. Look, you don't even have to look at your periodic table. It's in the bottom left right here. Atomic number is 6. Average atomic mass, let's just round it to the hundredths place off of our periodic table. I believe it's 12.01. Yes, it is. AMU. Oh, look, I wrote nicely this time. The mass number was given, right? So the mass number was given this time as 12. Now, there will be times where you have a mass number, you guys, that is not anywhere close to the average atomic mass. If you're given a mass number, like if we had carbon 14, we'd be like, oh, that's not a mistake, right? Like that's just a different isotope of carbon, a less abundant one. So there will be times when this mass number is not anywhere close to the average atomic mass, and that's okay. So don't let that confuse you. All right, so here's our mass number 12. I know I have 6 protons because that's my atomic number. My protons plus my neutrons have to add up to that mass number. That's going to be 6 as well. And no charge, same number of protons and electrons. And that's just a coincidence that those numbers are all the same, okay? The numbers of protons and neutrons being the same doesn't mean anything. The numbers of protons and electrons being the same does determine charge. All right, 1 more. Last one together, and then you'll finish on your own. Atomic number, you could look at the periodic table, or we could just look at this element symbol here. Lithium, atomic number of 3. Let's go find the average atomic mass for lithium. 6.94 AMU. I was given a mass number of 7. So this is the isotope that has 3 protons and 4 neutrons. These have to add up to the mass number. And this has a positive charge, a 1 plus charge. That means it has 1 more proton than electrons. So if I have 3 protons, I must only have 2 electrons. You lose an electron, you become positively charged. Gain an electron, negatively charged. You can gain or lose much more than one electron. Okay, so these charges can go all the way up to 4 plus and 4 minus. All right, so go finish this worksheet, and we will do an activity with this where you actually sort of visualize the numbers of subatomic particles that make up an atom. See you guys soon.